Hey, welcome back to Global Environment. We started to talk about a case study, Eritrea, last segment, and talked about how it has so many environmental problems and how do you look at that? Well, this is one way you can do it. You can use simulation models. And what is a model? A model is a formalization of our assumptions regarding a system. And if you think about what does it mean to formalize something, it's make it explicit. When we build these models, our assumptions become explicit. Now, why is that important? Because once we make them explicit, we can test them. So we're doing real science. Now, models are important because you can predict future outcomes from current trends or past trends. So again, the important part of science. Now, this model looks at population growth, agricultural expansion, agricultural yields, energy use, and deforestation. All major problems in this country. And it's a spatial simulation model. And spatial means it incorporates space. Some models punch out numbers. I'll show you what space means in this case. Now, for example, these are some of the inputs for the model. They go in as maps, digital elevation maps in some cases. Now, here are two examples of the input. This is a soils map of Eritrea. Each one of these colors represents a different soil type with different properties. This is a rainfall map of the country. Each color will mean a certain amount of rain. Green's high rain, red's low rainfall, and everything in between. So each one of these pixels has its own rainfall data. Now look at this. You've got soils, you've got rainfall. I had temperature maps, elevation maps, solar insolation maps. What could I figure out if I had all these maps? Well, one thing could be how much food they can grow and where they can grow it, and that's what I did. So these are the inputs, and they're spatial. I also use time series data, and you can see what happens as you add nitrogen fertilizer to wheat. And these are the yields here. Now, it's kind of interesting. If I was just an economist, I might expect you add more fertilizer, you get more yields. That isn't always the case. You can see this saturates out. Another interesting thing is my degree isn't in computing or environmental science. It's actually in biochemistry. And when I saw this graph, I got very excited because I recognized this behavior from enzymes. And I knew how to write a mathematical formula to explain this behavior and incorporate that in my model. So it's kind of funny how sciences can come together sometimes. So this was important data to use in the model. Now I had some assumptions. I was assuming that a country undergoing sustainable development could feed itself into the near future. And this country is very interested in food self-sufficiency. They are very proud fighting that 30-year war of independence. They don't want to accept food imports or handouts. They want to do it on their own. So, question, how many years could this country feed itself if they accepted no food imports? Now, I had to make certain assumptions in building this model because you can't get all the data you want. It's just impossible often. So you got to use what you have. So one of the assumptions is I only use 5 crops. But I think this isn't a bad assumption because 75% of their calories come from these crops. Now, I also assume that people take up no room. This is a ridiculous assumption. But what it does is any result I have is optimistic because people will take up agricultural land. I used Ethiopian response curves for fertilizer. I was forced to do this because not a lot of data exists for Eritrea since it's such a new country. And since it used to be the same country with Ethiopia, it might not be a bad assumption. I also used constant population growth rate. I made it smaller from 2.7, the current rate, to 2.4. So this program had certain subunits. It has a 1-year time step. It looks 100 years into the future. And it calculates population growth. That's the first thing it does. Then it looks at the amount of land you have to put in agriculture based on the population. More people, more land you're going to need. Then we determine where crops will be grown. For example, we use best first. Guys, why is it doing that? Okay. It seems like it has stopped. Why don't we... Well, now it's doing it again. No, I'm not pushing anything. My hands are... Huh? Let's see if these jump around. What I'm saying is it's not. So what I can do when we redo this is I can make these come out quickly. Okay, got it. Okay. Well, I'll go on. I know how to do it. Okay? Yes or no? Okay. Next, we have to determine where crops will be grown. It uses the best first principle. It looks for the best land, farms on that first, and then it goes to the next best land, and then the next best land. And then we have to determine the type. So if we're in high elevation, we might grow one type of crop, low elevation, another type of crop. And then it calculates erosion. Finally, it calculates total yield, and that's based on sunlight, rainfall, fertilizer response, soil fertility, and erosion. Okay. And in addition, the more land we put into agriculture, the higher the yield. So we're going to stop there, and in the next segment, I'm going to show you the output. We're going to look 100 years in the future and see what might be in store for this country. So I'll see you next time on Global Environment.